All right, so to evaluate the limits of piecewise functions, we have to look at them from the left and from the right, because remember what a piecewise function is. It's a function made up of two functions, and on the left of the partition you have a completely different function than on the right. All right, so we have to evaluate the left-hand limit and the right-hand limit at each partition, and same rules apply. If the right-hand limit and the left-hand limit are the same and they exist, then that's the limit of the function at that point. Okay, so here let's find each limit at x equals c, and then we have to evaluate the function at x equals c. Remember, finding the limit and evaluating are independent of one another. They have nothing to do with each other. Okay, so first we need to find the limit. So what we're going to do is we're going to say the limit as x approaches 3 from the negative side of f of x is equal to what? So now x equals 3 from the negative side. These are the numbers that are less than 3. So that's this realm, right? That means it's this function that I'm looking at. So I say that's going to be 2 times 3 plus 7, 13. Because it's 3 from the negative side, so it's the numbers less than 3. The limit, now the right-hand limit, as x approaches 3 from the positive side of f of x is equal to, now it's this one here, 3 squared minus 1, that is equal to 8. Because these are not the same, we say the limit of f of x as x approaches 3 does not exist. Yes. Okay, now to evaluate, right, that's part B here. What's f of 3? To evaluate, where do I put in the 3? To the top or to the bottom? To the top, because that's the one that has the equal sign, right? It's less than or equal to. So f of 3 is 18. Even though the limit doesn't exist, f of 3 exists and it's 18. I'm sorry, 13. I mixed up the 18 and the 3. I mean the 8 and the 13.
If there is a hole there, then there can't be effort.
Correct. If they were both open, then it wouldn't be. Okay, so now, okay, let's move on, and then I'll answer more questions. Let's move on. It's the next one, I promise. Let's just do that one. Okay, so the limit, okay, so look at this one. Now we're at -1. The limit of f of x as x approaches -1 from the minus side, we're going to plug it into this top one. So that's 1 plus 2 equal to 3. And then the limit as x approaches to -1 from the right side of f of x, that's 3 times -1 plus 6, that's equal to 3. So what do you think about the limit? It's 3, right? Because these are the same. Right, so now to evaluate f of -1, right? This one is open. I can't plug anything in there. This one is open. I can't plug anything in there. So it's undefined. For limits, we always do D&E. This is an open circle on top, so you can't plug anything in there. You can't plug -1 in there. And this is an open circle. And then I always get the question, well, what if they're both closed? Well, that can't exist, right? Because then it won't be a function, right? It won't pass the vertical line test. So that's a moot point. Okay. So take a look at this next problem. The width in millimeters of an animal's pupil is given by that function where x is the illuminance of light shining in the pupil, all right? So we know, for example, that based on like the ambient lighting, your pupils will either dilate or contract in order to take in the proper amount of light, right? So if it's bright, it'll contract and so on. So that's what that is. This is the width of an animal's pupils based on how much light is entering. Write a limit to describe the width of the animal's pupils when the light is at its minimum illuminance. So the light is at its minimum in illuminance. The light is given by what variable? X. So when the light is at its minimum illuminance, right? We're not saying there is no light. We're saying it's at its minimum. So this is the limit as X approaches 0. Okay? The illuminance is X. The light is X. So when we want the concept of the light at its minimum, it's the limit as X approaches 0. All right? Then find the limit and interpret your results. So what this is going to be is the limit as X approaches 0 of d of X, right? d of X is the width in diameters. I'm sorry, the width of the pupil. So this is the limit as X approaches 0 of that function. It's an actual equation. I'm not sure for which animal, but it's an actual equation. Okay. Now I need to evaluate this. So I've got, x to the negative point something, right? So let me see what all that looks like. So this is the limit as X approaches 0. Now, I can write that, right, X to the negative exponent as a denominator. So that'll be 152 over X to the 0.45, right, plus 85, divided by 4 over X to the 0.45 plus 10. Okay? This is equal to what now? I want to do a common denominator here on top and on the bottom. All right? So let's see if we could do that. So limit as X approaches 0 of, so notice I'm carrying the limit along, right? So the denominator in the top is going to be X to the 0.45. And then the numerator here is 152 plus 85 X to the 0.45. I just did a common denominator over here, right? So common denominator is this, right? So I just multiply top and bottom by X to the 0.45. Okay? Or I could do like a loop like this times that plus that. And then let's do the same thing on the bottom. So basically, another way to look at it is you can multiply top and bottom by this. Right? By the denominator of the other one. So now I get, what is this? X to the 0.45. 4 plus 10x to the 0.45. Okay, so this is equal to the limit as X approaches 0. Okay, so what have I done right now? I made the negative exponents into positive exponents, right? So look at this. I have the same denominator here as I do here. What can I do with those? Cancel them. So I have this, but that doesn't, let's see, over 4 plus 10 x to the 0.45. Okay? Now this is a nice simple polynomial equation. Now let's see if I could get away with finding the limit using direct substitution. Can I?
Yes.
What if I were to plug in 0 here? I get 152 on top. Plugging 0 here, I get 4 on the bottom. Okay? So, huh? Because I had, I would have gotten 0 in the denominator, right? 152 over 0. Look over there. Like, look 2 steps before. This is 152 over x to the 0.45. So I would have gotten 152 over 0 and 152 over 0. And I didn't want that. Well, even this is x to the negative. So it would have been 0 to the negative 0.45, which is 1 over 0. Okay? Yeah. So using direct substitution, this is 152 over 4, which is 38 millimeters. And now it says here, interpret your results. So what that means is, write a sentence in coherent English about what this means. Okay?
So you say as the luminance of light approaches 0, the width of the animal's pupil approaches 30.
Right. Exactly. So when the light, so basically when the light is at its minimum, the pupils have approach a width of 38 millimeters. Okay, coherent English sentence, but you've got some beefy stuff in there. The pupils approach a width, mathematical term, of 38 number, quantity, millimeters with proper units. You see that? Okay. Common answers I will find on a quiz or a test. Okay? Here's version 1. As the light is 0, it goes down to 38, or it goes up to 38. I have no idea what that is. What is it? What is it? What is it? We don't do pronouns, okay? The most it'll be is 38. Still, I don't know. The least it'll be is 38 when it's dark. I don't know what that is, okay? Say that again? So you said it. I can't use it, right? What is it? Okay? So you could say, so, right, so make sure you define those pronouns, yes.
You say like the people in the
right, but also avoid saying it will equal 38, right? Because it's a limit we're approaching. It'll approach its maximum of 38. Okay? All right. So now write a limit to describe the width of the animal's pupil as when the light is at its maximum illuminance. So now I want the limit as x approaches infinity for that one. Right, it does, because the quantity is positive, right? That's like distance, right? You sort of know by context that this is not going to be a negative number. It depends on the context. It depends on the context. In this prompt, okay, but here the infinity is not the width, it's the illuminance. Right, so, but like there will be problems where it will be negative infinity, so just watch for the context. Okay, So here I'm going to have the limit as x approaches infinity of that wonderful function. Yes. Yes. So. Right. Okay. So yes, that's what we're going to do. But listen, this function, look, this function here, when we simplified, there was no limit or anything like that involved. It was just like algebra 1 style algebra that we were doing, okay? So I could use this function from the beginning, the original one, and reinvent the wheel, or I could just say, you know what, each one of these steps represents an equivalent function. Let me just start with that one. So I'm going to start with that function here, step number 4, 85x to the 0.45 over 4 plus 10x to the 0.45. Now this time my limit is as x approaches infinity. So I'm going to do those rules, right? So I just look at the term with the highest exponent on top, the term with the highest exponent on the bottom. Oh my God, they're the same degree. So it's just 85 over 10, which is 8.5 millimeters. Okay, so as the light approaches maximum illuminescence, the pupil's width approaches a length of, or it just approaches 8.5 millimeters. That's good enough. Ooh, there's 10 minutes left. Okay, let's do this. Okay, molecular theory. Those of you guys that just finished AP honors, AP Chem, you should have seen this, okay? So the root mean square speed measures the average speed of a particle in a gas, right? In kinetics, okay, that's like one of my favorite parts in chemistry, by the way. And that's the formula, right? You don't need to know any chemistry to do this, but that's where it comes from. So this is the average speed of the molecules in a sample of gas. So it's V RMS, meaning the root mean square, is equal to this. R is the gas constant from PV equals nRT, Charles' law, Boyle's law, all of those laws. T is temperature, M is mass. Okay? So M is the molar mass of the gas in kilograms per mole. That's important. Okay? Now, find the limit of V as M approaches 0. So we're going to do, okay, the limit as M approaches 0 of this, okay? Now, 3 is a constant. R is a constant. T is the absolute temperature. That's a constant as well. So, okay. So these are constants here. Okay? So what I have now, okay, is basically a constant over a variable. What I have is a constant over M, which is like 1 over x, right? It's like the reciprocal function. So mathematically, when I'm going down the street and I see something like this on a billboard, oh, reciprocal function. As x gets very large, what happens to the whole thing? Gets small. As x gets very small, what happens to the whole thing? it gets very, very large. So now here, as m approaches 0, as m gets very, very tiny, what happens to the entire thing? It gets very, very large. And even the square root of very, very large is still very, very large, okay? So that will approach infinity.
No, but if it's approaching it from the negative side, you'll get.
How is it approaching it from the negative side?
So what I'm saying is, don't you have to spell?
We have to interpret our answer. So let's interpret our answer. And it says, hang on. It says as, okay, so as the mass becomes smaller and smaller and smaller, what happens to the speed? It gets infinitely large. That's what it is. And if you think about it physically, that makes a lot of sense. So as the mass of particles approaches 0, the velocity becomes infinitely large. Okay, now let's do the other version. The limit as m approaches infinity of v. So the limit as m approaches infinity of 3RT in a square root over m. Now, if you have something over a very large number, if you have one pizza and you have to divide it among 1,000,000 people, how much does each get? A minuscule amount. So that approaches 0. So now this is the opposite. As the mass of the particles get infinitely large, the velocity approaches 0. Okay, let's do limits of sequences. And again, right? This is 1 over something, so there is inverse proportionality. As the denominator gets larger, the whole thing becomes smaller. It is very important that you start to process that. If you're having trouble processing it, it's super, super important. Come to me, so one-on-one we can take a look at that. But it has to be eventually almost instinctive that you could do that. I'll take more questions on this later. Let me do the limits.
I have a question about the wording.
Okay, why don't we take it later? Okay. So we did sequences in chapter 10, all right? And we were talking about converging and diverging, and I had you manually plug points and like plot them on that graph. Do you remember? A sub n, and then you saw whether it diverged or converged. Well, guess what? That's like a whole thing in real life, in real math, except we do it using limits. Okay, so when you write a sub n, that explicit formula as a function, the limit of a sequence is the limit of the function. So if the limit exists, we say the sequence converges, right? So we did it graphically and numerically over there. We like laboriously found points, but now we're going to do it using limit stuff. If the limit does not exist, then the sequence diverges. So do you remember when, we had those points like this and we said it was something like that, it converged, and then if it wasn't, if it went up and down, it diverged? We could do the same thing using analytics, algebra, and limits, and we could get an answer like that. So take a look at this one. This is the explicit formula. And when you look at it as a function, it's a rational function. So all I have to do is say the limit as n approaches infinity, 4 over n squared plus 1. And now I follow the same rules. 4 over n squared, what is that? 0. So I say this converges. Now, I can't hear.
You not write the first 5 terms then?
Nope. I'm not. No. I wanted to do that so we could like compare, but I'm running out of time. But you guys remember from before how we did that. Okay, so here, the limit as n approaches infinity of this guy equals the limit as n approaches infinity. Now I'm going to take the stuff from the top and the stuff from the bottom. Remember, we do it when it's all multiplied out, but I'm not going to multiply it all out, so I'm just going to take like the first terms from each binomial, right? So this is 9 times n times 2n over 6. So that's the limit, 6n cubed, sorry. So this is the limit as n approaches infinity, 18n cubed over 6n cubed, 3 also converges. So that is your homework for tomorrow, part 2.